let us continue our discussion of the bounded variable transportation problem. So, I told you that we can work with a working basis. So, we spelled out that working basis of m plus n minus 1 basic cells, right, and your non-basic cells here can be your non-basic cells can be either at 0 level or at their upper bound level or at their upper bound. Okay. So, we will always maintain a basic solution of m plus n minus 1 cells, and the other, if there are other non-basic variables, they will be then at their upper bounds, and we said we will put a square around a non-basic cell which is at its upper bound to distinguish it from the other. So, now the optimality criteria again is the same that we discussed for the simplex algorithm for the LPP. So, here the optimality criteria would be Cij bar greater than or equal to 0 for non-basic variables Xij equal to 0, right, and it will be Cij bar less than or equal to 0 for non-basic variable Xij equal to Uij, right, because if it was positive for a non-basic variable at its upper bound, then by reducing the value of the variable from Uij to a lower value, I would have reduced the objective function value. So, therefore, the optimality criteria for a non-basic variable at its upper bound will be Cij bar less than or equal to 0. So, all that holds as for the simplex algorithm. Now, we said that how to get a starting feasible solution, because for the uncapacitated or the unbounded transportation problem, it was very easy to get a starting feasible solution. So, of course, one can use phase 1 to obtain a starting feasible solution. Okay, there are different methods, and later on I will give you a method which I consider is very neat, but we will have to wait for it because we still have to discuss that class of problems. So, that will help us to obtain the starting feasible solution, but here of course we can take recourse to phase 1, right. So, the phase 1 here would be simply that you will add artificial variable here and artificial variable here. That means m plus n variables you would have added, and so the transportation array. So, you add m plus n artificial variables, right. So, in phase 1 what will happen, see your array would look like this. So, you would have added, so here this is, and finally you will have here an m plus 1th column. So, let me so this is artificial variables. Okay, so this will be your m plus 1th source, and here you will have your n plus 1th market column row, right. Sorry, I am sorry, this will be m plus 1th row. So, this is a new this thing, and this will be n plus 1th market, right, because the constraints here you will have added plus x a I, right, an artificial variable for each supply constraint, and here if you like you can distinguish, and you can say that this is yj a equal to this. So, let us see, yes. So, for each destination constraint or market constraint, you have added an artificial variable and this. So, you see that this will be this, and here this will be this thing, right. So, then what would be your phase 1 objective function? So, phase 1 objective function would be phase 1 objective function. This would be minimize summation xai, I varying from 1 to m, plus summation yja, j varying from 1 to n. So, all other coefficients will be zeros, right, and these are the ones. So, we will work out, and the starting feasible solution you can immediately read off as xai is si and yja is dj. So, you will have this thing here, yeah, if you write this, right. So, this will become S1, S2 and so on. This will be 0, the last one here would be Sm, and then this would be D1, D2. So, you can read off your starting feasible solution to the extended problem like this, right, and here it will be Dn. So, these are the values, and this variable will have a 0 value, right, and these cells will have cost 0 except for the artificial variables. So, these cells will have cost 1. Oh, by the way, yes, okay, and this will have a 0 cost. So, why would I write 0 here? It will actually be the sum of this. So, this will be summation Si, right. So, because this all adds up to Si, and but the cost will be 0 here, right, and so this will also have cost 1 and cost 1. So, one can do the artificial variable thing here. You can apply phase 1, and once you end up with phase 1, that means you have no negative Cij bar in the whole tableau. Then you will stop with phase 1. So, if the as usual phase 1 objective function value is greater than 0, objective function I mean optimal, right. Phase 1, we mean by this that at the end of phase 1, whatever the objective function value, if it is greater than 0, problem is infeasible. Okay, and we will stop there. But if the objective function value is 0, then yes, there is a scope for that the problem is feasible. Now, it is possible that you may not have, yeah, so I can write out somewhere here, you may not have exactly m plus n minus 1. So, okay, if you want to keep the arithmetic right, see here in this case, we had how many cells here? You had the number of rows became m plus 1, number of columns became this. So, the total number became m plus n plus 2, and as usual, so therefore, number of basic cells is m plus n plus 1 initially, right. So, that is fine, because this is the extended problem. So, you will have that many. So, here you see, you can see, for example, this is n, this is m plus 1. So, m plus n plus basic cells you start with, right. So, if the phase 1, so phase 1 objective function value is 0, then it is possible that the number of positive variables from among the original variables, number of positive variables from among the original variables is less than m plus n minus 1. That means you, because there may be some artificial variables in the basis at 0 level, right. because the value of the objective function is 0. So, artificial variables, if they are in the basis, they will be at 0 level. So, we will drop those artificial variables, we will drop this row and this row and this column. So, then is this, then add 0 cells or add cells at 0 level, so that the solution is basic. So, just make sure, and you know that the way you will add the 0 cells, you make sure that there is no theta loop formed. Once you have that, then you have a starting basic feasible solution for your phase 2. Then you can remove the row and the column, and the prices you can work back withCij's, right. So, the so one can have a few simplifications here. For example, you would have to compute the Cij bars all over again, since you will have a new dual solution and this, so that can be done. For the simplex algorithm, we were able to maintain the other set ofCij's also, and therefore, when phase 1 ended, we could immediately start with phase 2. But here you will have to do some more bookkeeping to be able to do that, but fine, that is not a big problem, because anyway you have so much simplification in the problem. So, this can be done, but I would later on give you a better method for better in my opinion, it need not be better for everybody. So, I would like to give you another method for obtaining a starting feasible solution. Okay. So, that is for the starting feasible solution. Now, once you have, again simply a translation of all the rules that we worked out for the simplex algorithm for a general LPP. So, in this case here, if you have a working basis, how to proceed. So, you have a starting basic feasible solution. Suppose, so starting feasible solution exists, right. So, then you will compute your Cij bars, right, compute the Cij bars, the relative prices, and select. See here, there can be two opinions, because what is happening is that you compute the Cij bar and select the incoming variable, okay, fine. So, as Danzig says that you go for the most negative one, if optimality criteria is not satisfied, then Ci, and of course, in this case now you will have to look for either most negative Cij bar or a positive Cij bar for a variable at its upper bound, or a non basic variable, right. So, you will have to do this kind of scanning, or you can just select the first variable which will improve the value of the objective function. That means, you start scanning, and the first variable that first cell that you hit, for which the corresponding variable at 0 level and the Cij bar is less than 0, you can enter it. Okay. Now, it has been shown empirically again that Danzig's rule certainly gives you fewer iterations, because when you choose the most negative Cij bar or most positive Cij bar for a non basic variable at its upper bound, the decrease in the objective function value is quite large, and so the number of iterations are fewer as compared to your selecting the first cell which can improve the objective function value. So, empirically it has been shown, but then the thing is that you see here, when you have very large problems, to select the most negative or the most positive, you really have to scan all the cells and find out which one is the most negative or most positive. So, compared to the amount of work that you have to do per iteration and the number of iterations, so one can find out if the problems are very large, then maybe the first negative thing would be, or positive one, the first improving cell would be a better choice, because scanning will take a lot of time and the number of iterations, the amount of work required per iteration may be fewer, may be lesser, right. So, all those things, considerations are there, and they all come by practice and so on. So, so we will select the and compute the Cij bar and select the incoming variable. So, here we have two cases. If your Cij bar is less than 0, then again we will have three considerations, right. So, your theta loop, form the theta loop, containing Ij arc or cell Ij, containing cell Ij. So, choice for theta, choice of theta according to the following rule. So, theta 1 you choose as minimum of, see in the theta loop, remember we will start with plus theta here, then alternate with minus plus in the theta loop as we explained. So, this will be minimum of all theta, minimum theta such that xi, or maybe I should write something else here, xpqb minus theta is greater than or equal to 0. So, wherever the basic cell, the theta is with the minus sign, then this will change by xpq minus theta. So, you do not want this to become negative. So, for all theta such that this remains, so you choose the smallest, so that none of the current basis basic variables becomes negative, it can become 0, right. Then theta 2, same, I mean it is nothing new, it is just that I am repeating so that you understand the concepts better. So, theta 2 would be minimum of theta such that xpqb plus theta is less than upq. So, this you understand for the basic cells. So, for the basic cells, some of them will have plus theta, some will have minus theta in the theta loop. So, the plus ones, this value should not exceed their upper bound value, right. So, theta accordingly, that means here theta would be upq minus xpqb, and here theta would be less than the current xpq value, right. And finally, theta 3 would be, see, since Ij is going to enter the basis and it is going to become a positive number, because currently its value is 0, Cij bar less than 0. So, theta 3 should be your Uij. That means the incoming variable should not exceed its own upper bound. So, all these considerations we have already gone through while discussing the bounded variable simplex algorithm. So, then you choose your theta to be minimum of theta 1, theta 2 and Uij. And again, without spending time on writing down this thing, now you know very well that if the minimum occurs for, if the minimum is theta 1, then that means this particular variable for which the minimum occurs will become non-basic at 0 level, and your Ij cell will become a basic cell. If this happens, theta 2, if theta 2 is the minimum of the 3 numbers, then the corresponding basic variable here will become non-basic at its upper bound, right. So, we will put a square, we will remove the circle, put a square around it, and the incoming variable will be a basic variable. So, again you have a change in the basis. If the minimum is Uij, then that means the status of the Ij cell will not change, it will remain non-basic, but it will be at its upper bound, right. And the basis, the original basis remains, it is just that you again now put a square around the Ij cell to indicate that it is a non-basic variable at its upper bound. Similarly, you can argue out for Cij bar greater than 0. So, here we will say that when Cij bar is greater than 0 for Xij at its upper bound, right. So, Cij bar is positive. So, there is a scope, because when I reduce the value of Xij from its Uij value, since this is positive, there will be a decrease in the objective function value, and so there will be an improvement, right. So, here again, here what you will do is you form a reverse theta loop. Right, which means that you begin with minus theta in cell ij and alternate with plus theta and minus theta in the loop, right. So, you form a reverse theta loop, that is all you have to take care of, and then again it is the same exactly. So, and then compute the minimum value of theta such that no current basic variable becomes negative or violates its upper bound restriction, right, and the incoming variable and the outgoing variable, say for example, I should not say outgoing, and the value of Xij should not become negative, So, the same values will be computed. There will be Uij, because this Xij value you are reducing, right, you are writing Xij minus theta, because you are beginning the loop with minus theta. So, this should not become negative. That means theta should be greater than well, sorry, this should be this is Uij. Your currently your variable is at its upper bound, so this is Uij. So, therefore, theta should be this should not become negative. So, this will remain this, right. So, which implies that theta is less than or equal to Uij, right. So, here the same considerations, you will have theta 1, theta 2 and theta 3. So, how you will choose the best one, and accordingly you will decide whichever the minimum occurs, you will decide whether the incoming variable is is going to be at 0 level, or it is going to become non-basic, or whatever. Well, in this case, yes. So, you can decide all that, right. I think that makes the algorithm quite clear. We have already gone through the whole thing in the general case, and it is just the simplifications which I thought I will point out. Okay. So, now let us go through this example. I thought I will show you the steps. So, here for example, you have a bounded variable transportation problem. Each Xij has to be less than or equal to 15. These are the supplies, these are the demands, and I show you initial starting feasible solution. Okay. So, here for example, this is non-basic variable at its upper bound. Otherwise, you have a working basis. So, 1, 2, 3, 4, 5, 6, right. Your m plus n minus 1 is 6. So, I have a basic feasible solution and one this thing. So, now we quickly compute the dual solution. So, I will put this as 0. So, I can immediately get this value 4, 2 and this is 3, right. This is a non-basic variable, and now you can come here. So, this will be 0 again, because 2 plus 0 is 2, then this will be 3, right, and what else? Yeah, once you have this, then this should be 3. So, this is your starting dual solution, okay, and let us compute this. So, this is minus 2, 2 minus 4 is minus 2. So, like as I said, one could have just started from here, but since it's a small problem, we will see if we can you follow Dan6 rule. So this would be 3 and 11, so no problem. 7, this is 1, then 5, this is 4, and here it is 6, so 10. And for this one, remember, this is the non-basic variable. So here this is 12 minus 3, which is 9. So you see, it will improve, it will help to, so we will choose this one. As I said, I could have selected this as an incoming variable, or I can go for this one, right. So here you form the theta loop, and you see that you immediately have this is as this, and this, right. But here it's going to be minus theta plus theta minus theta plus theta. So if you compute the 3 values, see here, for example, theta 1 is 11, that's the only one, right. Then these 2 values here, this should be, so theta 2 is 4, because otherwise this variable will exceed its upper bound. And here your theta 3 is 15, because this should not become negative. So I'll choose this one, right, theta 2 equal to 4. And so what will happen is that this will become basic, but this will now become non-basic. So let's quickly do it, and this number will become 7. So 4, this becomes 9, and now this becomes a basic variable at level 11. Okay, and let me get rid of this loop here. Okay, yeah, these values also go away. So this is 12. Okay, and this one becomes now a non-basic at its upper bound. So this is your new basic feasible solution. Yes. Okay. So we quickly compute. Now in this case, you really have it easy, because 4, 2, and this becomes 12. That is 3. So I simply have to compute. So this will be this will remain the same, right? And yes, and here this one will be your 3, right? So these numbers will not change. See, it's only this one which will change, because these numbers and these numbers are the same, so I don't have to compute them. And here what will happen, 12, 15, this is still 1, and what will be this number will also not change, because this is 11. Yes, I have to compute for this one, so this will be 3 minus 12, which is minus 9, so that's fine, and we are done. Yes, so just 2 iterations, because I chose a small problem. Would have liked to show you another iteration, but doesn't matter. So it turned out to be a small problem, and optimality conditions are satisfied. So this is your bounded transportation problem. Okay. So once we have done this, I would like to now go to your general min cost flow problem, which I had stated for you right in the beginning, and then I said that the transportation problem is a special case, because the underlying graph becomes bipartite for the transportation problem. So things become simpler, and now let us look at, I already showed you what were the considerations. So there's not much change, except that, see, we will go through it so that you become familiar with the graph terminology, because for the transportation problem we could translate everything to the array. So the graph was not at all, we were not referring back to the graph, though you should sometimes just draw the bipartite graph and trace out the basic feasible solutions on the bipartite graph. You can do that. I did not do it, because of course we want to cover few more topics. So now for the general min cost flow problem, where the underlying graph need not be bipartite, we will have you will see that of course the algorithm is the same, the simplex algorithm, the simplifications are there, but then now we will be working with the graphs as the basic structures. right, instead of this array. So, min cost flow problem, we had defined it as minimize z equal to summation Cij Xij, where our arc ij belongs to A, subject to summation Xij summation j minus summation Xki summation over k is equal to Bi, I varying from 1 to n. And the general problem, this will have Xij is less than or equal to Uij, where again Uij may be finite or infinite. Okay, that means the infinite case means the arc has no upper bound restriction. So, I had talked to you that the basic solution here would be a tree. I defined to you. The tree is a, or not, sometimes I will use that tree or a spanning tree. It's the same thing. I mean, the same thing is that I'll be using them synonymously, but of course, a spanning tree is a connected. I'm just repeating this definition: connected subgraph subgraph with no cycle, right. So, we said that should have n minus 1 arcs. Okay, so, a spanning tree will have n minus 1 arcs, there will be no cycle present. I had defined all these things right in the beginning when we were talking about it, right. So, here again that means you want to find a we can see that the simplex algorithm gets simplified here because of the structure, and yes, n minus 1 arcs and all this because the rank of the coefficient matrix is n minus 1, and we showed you again it's the same structure because the transportation problem your columns were ei, ej, because I could get rid of the minus sign, whereas here if an arc ij appears here with a plus sign, so you see for the jth node it will appear with a minus sign. So, the column, because so here your aij would be ei minus ej, right. So, triangular bases and everything, all those things hold here. I had shown to you all these things in detail in the for the transportation problem. So, we will say that the basis is triangular, yes. So, basis is triangular, all that things, and the rank, that's for, because you could do it with ei, ej, you could show that the rank is n minus 1. So, here also you can immediately show that the rank is of the matrix is n minus 1. And of course, I should have put the condition here that summation Bi is 0. So, this is important, we are always working with this condition, right. Now, you see for the uncapacitated case, suppose all uij's are infinity, that means there are no restrictions on the you can send as much amount as you wish. The problem can be reduced to a transportation problem. See, they are all related, and that's why and so you can take the advantage of the structure. And so, how will you do that? Yes, see, what you can do is in the this thing here, it's possible that some bi's may be 0, and see, it's a very general case. So, some arcs, some nodes may not have anything, any supply or any demand. So, they would be, and we call them transshipment points also. This term comes along. Say for example, I have drawn this graph for you. So, here there is amount available, 5 units available at node 1 and at node 4. So, they will be treated as our supply points, and here at node 5 and node 6 amounts are demanded, right. But 2 and 3 have no amount, this thing available, or no amount to be demanded, right. So, we will call these as transshipment points. So, I am now considering the case when all uij's are infinity, and I want to show you that this problem can be reduced to a transportation problem. In fact, it will be I am saying reduced because the size of the transportation problem would be smaller. And what do we do here? We say that you allocate a row for each supply node and allocate a column for each demand node. So, for example, you have nodes 1 and 4 as the supply nodes. So, therefore, one row for node 1, another row for node 4, and then nodes 5 and 6 are the demand nodes. So, therefore, this column for the node 5, and this is the column for node 6, right. Now, how do we determine the cost? So, for example, I need to know the cost C15, and so what we are saying is that you will choose C15 as the cost of the shortest path from 1 to 5. And this is again my idea is to show you how the size can really explode. So, now for this small problem, you see the possible paths from 1 to 5 are 2 to 4, 6 in number, and please for yourself sit down with that network and see which are the paths which have these costs. So, I think there should be no error here, and then I will choose the minimum one here. So, this is 2, and you will need to of course somewhere write down which is that path, because later on you will have to. So, for example, here I did not make a note, but you can quickly see that the path from 1 to 5 would include so if you come here this way 2 to 4 minus 2, right. So, this 2 1 to 3, 3 to 4 and 4 to 5. So, this 2 and minus 2 will cancel, and therefore, the cost will be 2. So, this is the smallest path, right. So, from here you are going this way, and I will indicate the path here. Okay. So, this will be the shortest path, and the cost therefore will be 2. So, I have put it down here. Then similarly, C16 cost of the shortest path from 1 to 6, and here the number of paths is 2, 4, 6, 8. So, please figure out which are all these paths. I have written down the cost. So, minimum cost is 3, and here also you need to figure out which is the smallest cost here. Say for example, 3 to 5, 5 and then minus 2. So, this will be 3 and 4. Sorry, minus 2 to 3, that becomes 4, but my cost is 3. So, the path will have to be short. Okay, maybe if you do it this way, 3, see I need to use that minus 2, right. So, if you come this way, right, then 3 plus 4, 4 plus 2, 6, again it is coming out to be minus 2, and then this will be 1. So, that will be 5. Okay. So, we will have to figure out which is the path really which gives you okay, fine. This will be 3 1 4, 4 and 2 6. Again this will be 6 minus 3 4 2 6, 6 minus 2 would be 4, 4 1 5. So, that does not help you. Okay, 2 1 3, right, no, okay, fine. So, then please figure out which is the shortest path, 3 1, because this will become 6. So, okay, I have somehow computed, maybe there is an error here, but just make sure that okay, in case this is the minimum path, the cost is 3, or if it is not, then you write the right path, but I will show you the calculations with this one. So, the current solution is optimal. I should have written out the path here. And now, you see once you have these costs, let me use the northwest corner rule and make the start with a basic feasible solution. So, here I can allocate 5, because the minimum of 5 and 6 is 5. Then I will come down here, allocate one more unit here, and then you go this way. So, then this becomes 5 and 5. So, you have this 5 here. So, this is your cost, right. And then you find out the dual solution. So, obviously, I will make this as 0. U2 as 0, and then that gives me yes, minus 2 minus 1 is, that is obvious, because when you want to know the thing from 4 to 6, 4 to 6, 4 to 5 is minus 2, and 4 to 6 would be 4, 5 and 6, right. This will be the path, right. So, that will be minus 2 plus 1 minus 1. So, these are the shortest paths from the supply point 4 to the two demand points 5 and 6. So, So, these are the two costs. So, therefore, my reduced this thing is there, the reduced transportation problem is there, and now I can apply the transportation algorithm. So, as I said, we will find out the northwest corner, will apply the northwest corner rule to get a starting solution, but it turns out that when you write down the dual variable. So, this is 0, and therefore, that will make these two as -2 -1, and then from here you see that this will be 4, because 4 minus 2 would be 2. So, 2 minus 2 would be 0. So, this is your dual solution, and then when you compute the cost of this cell, it is going to be 4 minus 1 is 3. So, 3 minus 3 is 0. So, you have an alternate optimal solution. Okay. So, this is when my this cost is 3. If it is different, then you please make the computations make the calculations correct. So, anyway, currently there is an alternate optimal solution, right. But before I go to the alternate optimal solution, we can quickly interpret this solution now. So, that is why you need to record the shortest paths somewhere, because if you have a larger network, then you simply show that 1 to 5. So, along the shortest path 5 units go, this and this, as I told you, 5 units, and then this is from 4 to 6. 4 to 6 the path was this one. So, 1 unit along this path, right, and then you have 4 to 5. 4 to 5 you have 5 units along this, right. So, this arc gets used the maximum number of times. Anyway, so once you have the optimal solution to the transportation problem, you can go back and distribute the flow along the arcs to get the actual flow on the network, right. And then with the alternate optimal solution, you will have to form a loop like this, and then you can see that if this is theta, this is minus theta plus theta minus theta. So, anyway, theta comes out to be 5, and therefore, this will be 5 and this will be 6, and you will have a degenerate basic feasible solution. So, you can treat one of them as a basic variable, the other one you can drop out. So, this is the idea behind, and if you have capacities, if the uij's were finite, as I said here, if the uij's are finite, then the problem can be formulated as a bounded transportation problem. And what will we do? For example, to compute U15, you will do it as the U15 will be the minimum of the. So, the paths you had from 1 to 5, whatever the path, you will take the minimum capacity of all the arcs in the path, right, and that will be your U15. So, you can immediately compute the capacities of the arcs in the reduced transportation network, and so you will then handle the problem as a bounded transportation problem. Obtaining a starting feasible solution will require some consideration. So, that is the only difficult point that gets added. Otherwise, the implementation of the simplex algorithm, as you see, is really quite simplified here. So, let us get back to the general solution here. So, how do I will just spell out the steps of the algorithm, and then we will work out a numerical example to again show you the steps of the algorithm. So, here so a basic feasible solution to the min cost flow problem will be denoted by TLU. Okay, and let me explain. So, T is the set of basic arcs, right, the set of basic arcs that form a spanning tree. Okay. Then L denotes the arcs at the lower bound, which is 0 here, right. See, we could have a general situation where even your lower bounds are not necessarily zeros, but we will first discuss this case, and then once you understand this, then you can handle with a little modification, you can handle the case when the lower bounds are also different from zeros, okay, but which is 0, and u denotes the arcs which are non-basic and at their upper bounds. Okay. So, this is the kind of thing we will always maintain, and when you modify your current solution, then some things will change here, your tree will change, or arc will go out or come in, or non-basic variable here becomes reaches its upper bound, it does not. So, all those things will happen. We have already seen this in the terms of transportation and bounded transportation problem and so on, right. So, but let me just give you now a feeling as to what happens. See, the thing is that, yes, and you will compute the fine. So, let me write the dual, and then again not much different from what we have been doing so far. So, here the dual same thing, because a column has EI and minus EJ. So, there will be UI and VJ, let us say, or in fact, here we are not having two different sets of dual variables, because your node set is not divided into two subsets. So, it will be the same set of this thing. So, let me call here the dual problem we will define as maximize psi equal to summation. So, this is Bi Wi, I varying from 1 to n, right. Yes, n nodes. So, you have this subject to, so it will be Wi minus Wj less than or equal to Cij, and yes, I am not explicitly considering these constraints. So, then your Wi greater less than 0 for all I, for all nodes. Okay. So, this is your dual problem, and same thing you need to determine n dual variables, but equality constraints are n minus 1, right, because corresponding to each basic variable, the dual constraint must be satisfied as equality, right. So, we will have n minus 1. So, fix one of the dual variables to value 0, and mostly. So, we decide to choose W1 to be 0. So, we just keep that convention. Okay. So, W1 will always be 0, and again, because of the triangular nature, I had already spelled it out for you in the simplex algorithm for the transportation problem, that it does not really matter what value I give to W1, as long as I give it some constant value, the relative prices will not, because all the Wi's will change by the same amount, whatever the value of W1, right, because of the triangular nature, right. You can see that, or sit down, and I showed the computations to you for the transportation problem. So, therefore, the relative prices will not change no matter what. So, for ease of, for convenience, we choose W1 to be 0. Okay. So, you will do this, and then we will compute the, and then so compute Cij bars, right. And here the same considerations, if Cij bar, the optimality criteria would be compute this, and you know the optimality criteria, Cij bar should be non-negative for arcs which are at 0 level, and Cij bar should be less than 0 for arcs which are at their upper bounds, non-basic cells, right. For the basic cells you have equality. So, optimality criteria also you can spell out, optimality criteria you can spell out, right. So, therefore, how do I now obtain a new basic feasible solution? So, going through this example for the min cost flow problem, as here currently see these numbers are the BIs. So, they must again add up to 0. So, this is 6 and 3 9, and this is minus 4 minus 3 minus 2. So, sigma BI is 0. These numbers, the first number is the capacity of the arc and the second number is the cost of the arc, right. And I have a basic feasible solution shown in this network, and accordingly you see your tree. The tree of basic arcs consists of 1 comma 3, 1 comma 3 which has a flow of 3 units, 2 comma 3 the arc 2 comma 3 which has a flow of 1 unit, then 2 4 has a flow of 2 units, and the arc, oh this is 5 2 not 2 5 5 2. So, 5 2 has a flow of 3 units. You can see that all the demands are met and all the supply is used up at at the supply nodes, right. You can check from here. Then, so the notation that we are using is our basic feasible solution is denoted by T comma L comma U. So, the arcs in L are the non-basic arcs at 0 level, and the arcs in U are the non-basic arcs at their upper bounds. So, currently this broken arc indicates the arc which is at its upper bound, but it is a non-basic arc. So, the flow is indicated by the square around the number to indicate that it is a non-basic arc at its upper bound, right. Then we need to compute the dual solution, and you can see that for the dual solution for the basic arcs this will be 0, right, for basic arcs. So, we start with this W1 as 0, then you can see from here, because this number has to be 0. So, for example, for 1 3 the cost is 3. So, this will be 3 and W1 is 0. So, then plus W3 is 0, right, which gives you that W3 is minus 3. So, this is how the number is indicated. Similarly, you can compute W2, W5 and W4, right, because from here along this arc the cost is 1 and then along arc 2 4 the cost is 0. So, you accordingly you can compute the remaining dual variables. So, the dual solution is indicated here, right. Now, you need to check whether the current solution is optimal or not. So, we will verify the we will check the optimality criteria. So, for example, for arc 3 5 which is a basic non-basic arc at its lower bound, the C bar 3 5 would be C 3 5 minus W1 plus W5. So, which will be accordingly for 3 5 the cost is 0. So, 0 minus of W3 which is 3, and then 5 W5 is minus 3. So, this is 0, right, and therefore, this indicates an alternate optimal solution. C bar 4 5 it will be C bar 4 5 will be 1, the cost is 1, then plus this was 4 5. So, this is minus 4, so becomes plus 4, and this is minus 3. So, 5 minus 3 2 greater than 0, again optimality criteria is satisfied. And for C bar 1 2 the cost would be 5 minus 4, C bar 1 2, yeah, because this is 0 the cost is 5. So, 5 minus 4 is 1 which is greater than 0. So, when you reduce the flow on arc 1 2 the cost will come down, right. So, therefore, the current optimality criteria is not satisfied, and so flow on arc 1 2 can be reduced, right. So, then we will determine the orientation of the cycle, because you want to reduce the flow on arc 1 2. So, therefore, the orientation is this, and if I want to do the update the flow by theta units, then on this arc it will be minus theta. 1 3 has the same orientation as the cycle, therefore, the flow will go up on arc 1 3 by amount theta. Again arc 2 3 is against the orientation of the cycle. So, our flow will reduce on arc 2 3 by theta. So, therefore, minus theta, and now since you want the new solution also to be basic feasible, therefore, theta can be at most equal to 1, right. So, the value of theta comes out to be 1, and now you need to update the flow on the tree, and you see that arc 2 3 becomes now a non-basic arc at its lower bound, because the flow has reduced to 0. Arc 1 2 is now becomes a basic arc, because the flow on it is not equal to its upper bound. The flow comes down to 2 units, and I have indicated the new updated solution here, which is, so on arc 1 2 the flow is 2 units, these two flows did not get disturbed, flow on arc 1 3 has gone up by 1 unit, so that becomes 4 units. Okay. This is just translating whatever we did, I mean the network, the simplex network algorithm that we discussed. So, I am just trying to translate it through this example, and now of course, let us compute the new dual solution. So, once you take this 0, this will remain minus W3, well, W3 is minus 3, right, and now you need to do it for this 2, and that 2 came out to be, see here again the same thing, you can do it in the same way, because this thing is, the cost is 5. So, 5 and plus W2 is 0. So, W2 will be minus 5. So, in this case this will be minus 5, and then for arc 2 4, what are the numbers? The cost is 0. So, 0 plus 5 and plus W4 is 0, right. So, W4 is also minus 5, which makes sense because the cost C24 is 0, right. Even here also it was minus 4, as long as this is the basic arc, this is what will happen, right. And then for arc 5 2 also it should not change. For arc 5 2 the cost is 1. So, 1 5 2. So, therefore, this will be minus W5 plus W2, which is minus 5 is 0, right. So, W5 will be 4. Hold on, what do I want to write down here? See, I want to say that 0 is equal to C52, and then this becomes minus W5 plus W2, right. So, W2 is equal to minus 5, C52 is equal to how much? C52 is 1. So, 1 minus W5 minus 5 W2, right. So, W5 is going to be 4, okay, that is okay, minus 4. So, this is that shows you that minus W5 is equal to 4. So, W5 is minus 4. You see, the positive number should did worry me, because see, this is minus 4, when you take it to this side becomes 4. So, minus W5 is 4, therefore, W5 is minus 4. So, you must sort of build your own checks while you are doing the computation, right, and you can now verify the optimality criteria. I mean, do it, check for optimality, and if you see that it is still not satisfied, then you will determine the incoming arc, and you will try to then determine the orientation of the cycle, determine the value by which you can update the flow, right, and then continue till you satisfy the optimality criteria. So, this is the idea. I took a small example to show you that how by exploiting the structure, and you can really simplify the network simplex algorithm and get a reasonably efficient algorithm to solve these network flow min cost flow problems. Okay.